Okay, this is 2023 AP Physics C Mechanics free response questions set 2, number 3. I put the other two up already. Again, first go around at these, so are mistakes possible? Absolutely. So just, take it with a grain of salt. And this is what I think. I could be wrong, but this is what I think that you would do on these problems. All right, we've got a wind turbine, and we've got a 3-blade system that rotates about an axis through the end of each blade as shown above, and each blade has a length L and mass M with the center of mass located at L/3 from the axis of rotation as shown in figure 2. Derive an expression for the rotational inertia of the 3-blade system. Express your answers in terms of M, L, and physical constants as appropriate, and the rotational inertia about each blade about an axis through its center of mass is given by this equation. But my axis of rotation is moved over here. So I'm going to find the eye of one blade, okay, because they're all the same. So if I find the eye of one, I can just multiply by 3. And I'm going to use the parallel axis theorem. So if you remember the parallel axis theorem, it's I is equal to I com plus mh squared. So I is equal to I through the center of mass, which is 1/18 ml squared, plus the mass of the whole thing, which they tell me it has a mass of m. And h, remember h is the distance from the axis of rotation to the center of mass, and they tell me that's L/3. So I get 1/18 ml squared plus, this gives me ml squared over 9. I need a common denominator for those. Looks like 18's my guy. So let's just do this. Let's say 18 here and 2 here. 2 plus 1 is 3, so I get 3 ml squared over 18, or ml squared over 6. Now remember, that's one blade. How many blades do I have? The eye of the system is going to be 3 times the eye of one blade, because I have 3 blades. So 3 times ml squared over 6, or ml squared over 2. And that is my eye of that system. Okay, now let me move some stuff around over here that I got going on so I can have a little room. Okay. While the wind blows, the 3-blade system operates at a constant angular speed, oops, you probably can't see that, of omega naught of 2.6 radians per second. The length of one blade is 36 meters. The numerical value of rotational inertia of the system is this. So that thing that we just found, they got a value for it. Calculate the time t it takes the outer edge of a single blade to complete one revolution. Well, to make one revolution, we want the period. So one revolution is 2 pi radians, right? That's all the way around. And omega is 2 pi over the period. And it says it's a constant angular speed, so it doesn't change. So my period will be 2 pi over omega. So 2 pi over 2.6 radians per second. And that gives me 2.42 seconds. And there's my period, or 2.4 significant digit wise. I'll just knock that off. There we go, 2.4 seconds, that's my period. All right, when the wind stops blowing, the angular speed, of the system decreases. The angular speed of the system while slowing down is given by this formula, where beta naught is a constant with appropriate units as shown in the figure 3. Calculate the amount of energy dissipated from time 0 when the wind stops blowing until the system comes to rest. Well, this thing is rotating. So the energy it loses is the energy that it has, because if it stops rotating at the end, it has no energy. So we need to know kinetic energy in the beginning to tell us how much is dissipated when it does this. So in the beginning, we have 1/2 I omega squared, and that's what we're going to lose. So 1/2 times that I value that they give me of 6.67 times 10 to the 6 times the omega, which is going to be omega naught, which is 2.6 times e to the negative beta naught times the time, and this is at the beginning, so it's time 0. Well, what's anything to the 0 power? 1. So this goes away. This is squared. So 0.5 times 6.67 times 10 to the 6th times 2.6 squared. And I get 2. I had 3 significant digits in the 6.67, so I had 2 in that one, so really 2.3, but I'm going to go ahead and carry it out this far because they're not going to really care. 2.25 times 10 to the 2, 4, 6, 7 joules. That's how much I started with, so that's how much is going to get dissipated. I think they would be okay if you did an energy final minus energy naught, and you did 0 minus that to get a negative number, so 2.25 times 10 to the 7th. So negative 2.25 times 10 to the 7th. That's your delta E. That's your change in energy. But I don't think it matters here because they just say calculate the amount of energy. They just want to know how much, how big, what magnitude. Okay. Derive an expression for the net torque exerted on the system as it slows down and express all your answers in terms of the following. Well, torque is equal to I alpha. And they told me I can use I of the system, so I don't have to plug that number in. But I need alpha. Well, alpha is the derivative of velocity because alpha is acceleration. So we're going to do the derivative of this business, which is omega naught e to the negative beta naught times t. We're going to derive that. Omega naught is a constant, so it stays. E, the derivative of e to anything is e to the thing times the derivative of the thing. And with respect to t, that's the derivative is negative beta naught. So I get negative beta naught omega naught e to the negative beta naught t. And that's my alpha. That's what's going to go here. So negative beta naught omega naught e to the negative beta naught t. There we go. And that is my net torque as a function of time. Okay. This one's kind of ugly as far as, letters. There's a lot of letters, but if you just don't panic, it's doable. Derive an expression for the angular displacement. Okay, now we want delta theta. Gosh, if I want delta theta, well, velocity is d theta dt. So if I separate my variables and I integrate, I get delta theta is equal to the integral of omega with respect to time. So that's what we're going to do. We're going to integrate. So delta theta is going to be the integral of omega naught e to the negative beta naught t dt. Now, if you want to, you could take out the omega naught times the integral of negative beta naught t dt, and then you can integrate that. I think, yeah, they have it right here on your equation sheet. So if you forgot how to do this, I was like, I think it's on there. There it is right there, e to the whatever here. Now, we're doing t, not x, but you could take this and you could figure it out if you can't remember. So this is going to be omega naught times e to the negative beta naught t over that negative beta naught, because if we do that, we've got to take, when we take the derivative of this, we'd multiply by the beta naught, it would cancel, and then we end up back to the same place. So this is my delta theta. Wondering if I need to go a little farther with that, because I'm thinking about it. I'm like, well, it's delta theta is from 0 to t, so if we do that, evaluate from 0 to t, let's see what happens. We get omega naught e to the negative beta naught t over negative beta naught minus omega naught e to the negative beta naught times 0 over negative beta naught. Oh, we do got to do this. Okay, because this one goes to 1. That's what that becomes, because e to the 0 becomes 1. So that goes away. But I've got this, and I've got negative, negative, so that's a positive. So my delta theta is going to be omega naught over beta naught minus omega naught e to the negative beta naught t over beta naught. And there's my delta theta, I believe. Sorry for that being so crowded. I tried to cram it in the little space that they provide there. All right. Now, it says now we're going to change it. This one's going to slow down to another function where this time the beta is a little bigger than, this was beta naught, now it's beta, and this is bigger than that. So if I write this as omega over e to the beta t, that makes it look a little better. Okay, if this is bigger, then every time I go along, this is dividing by a bigger number. And so instead of ending up at the same place, I'm going to end up a little below it every time. And so we're going to start at the same omega naught. Let's see. Yeah, we're going to start at the same omega naught, but we're going to decrease a little quicker and head to 0 a little quicker. Well, if I can turn the page. That may be it. That is it. We are done. Stop. End of exam. So hopefully this helps you. Again, it's my first time on it, so I may have made a mistake here or there, but this will give you guys an idea of what I think I would have done.